Okay, so hey guys, welcome back to another maths video. So today we're going to be looking at the start of a series on integration, which is essentially the opposite operation to differentiation, which I've shown you before in previous videos. So this is going to be like another series. I'll keep it quick in this short one, just explaining what it is and a basic method of doing it. So here I've got a little poster which I'm just going to speak through with you because it's not the clearest by itself, and then I'll show you some examples about how to do integration. So integrating a function, which is what we're going to be doing, is finding its antiderivative. So essentially it's the opposite of differentiation, which we looked at before. And also if you plot the function on a curve, instead of finding the tangent to it at the slope, that's gradient, you can find the formula for the area under a curve as well. So it'll give you a new function with input x, and you can choose two values of x. You could choose them to be b and a. And you put it here and here after this weird curve bar thing. You write a dx as well, or d and whatever variable you're integrating with the function. So x usually, and it comes out a function. And usually you write plus c, and I'll explain why in a minute. And you can get a formula for area, which you just substitute in b and a. And you take them, find the difference, and you can work out the area. So it's really cool like that. And you can have indefinite or definite integration. So basically, if you just want the formula to substitute in b and a into to find the area, but you don't actually want to substitute any values in b or a, you just want the general formula for functions. Basically, it's integral. You need a plus c at the end, and you don't include the b or a. And the reason for that is plus c represents any constant number, so nothing to do with x. And you may remember, let's move on to paper. If we have a function, so f of x here, f, and we say that's equal to x squared plus 6. We could say g of x is equal to x squared plus 7. If I take the derivative of f of x, so f dash of x, you could tell me, that's going to be, both terms we're going to get 2x, and the constant disappears and becomes 0. And again, g dash of x, constant disappears, we just the x squared becomes 2x. So we have both the same derivative. So if we was to reverse that and look at 2x and say what function is this a derivative of, so basically integration, we get the 2x and say, oh, that's came from x squared. But we're not going to get the plus 6 or the plus 7 back. We're not going to be able to tell what that constant was. So we basically, in integration, indefinite, you write a plus c at the end to represent that missing constant that could have been at the end of an integration. But we don't do that in definite integration with the b and the a. And the reason for that is, let's say you have a function f of x, no dash, sorry, just f of x, and we integrate that between the bounds b and a, dx, you have to write that. That's going to give us a function capital F of x, let's say, plus c. So, and to work out the area under the curve between b and a, you substitute b and a in and you find the difference. And what you're going to do is you're going to do capital F of b plus c, so all that minus capital F of a plus c, brackets around that. And what you notice is when you work this out, it just becomes capital F of b minus capital F of a. The c's cancel, so it doesn't matter what you don't need to write the plus c because it's going to disappear anyway when doing definite integration, right? Now, integration is a lot harder than differentiation because it's not as simple and methodical. There's different techniques you can use, but it's about getting it into the right form to spot the antiderivative. So that's why it can be really hard. I'm going to go through different methods in videos. It can get a lot more complex. But at the minute, let's look at the nicest function you can have, a polynomial. So with just powers of x. And the formula for integrating a polynomial, you use the power rule, which essentially, if we have indefinite integral of ax to the n, a is just a multiple, constant multiple, dx, we just write ax to the n plus 1 divided by n plus 1 plus c, of course. C has to be a real number and not n has to be not minus 1. I'll talk about it in a bit. Now you can see this is just the inverse of the differentiation power rule, essentially, where instead of taking one from the power and times it by the new power, let's say that the power is n, and let's say that some number n is n minus 1, right? So if we get a function f of x and we take its derivative, f dash of x, this was some thing ax to the n, right? And its derivative is going to be instead a, because constants don't change, x to the minus 1, and we times it by n, the original power. We bring that down. N minus 1, we can just call that m. So if, let's say, we want to take the antiderivative of f of x inverse, work out f of x, well, we're going to add 1 to the power. So it's going to be n plus 1. We're going to go back to n again, because that's what we want to get back to ax to the n. So we want to turn n back into n, and we have to add 1 for that to work. So it's going to be a, because constants can be taken out of integration as well. That same principle. To the n, because we've added 1 to m. That makes sense. Or n plus 1, as it says, that is n. And we divide, because we need to divide by n, because that's what we've got in front. And that is actually n plus 1. Again, so the power, we have to divide by the new one instead of the old one, which may seem strange, but it does work. So that is the power rule. And remember, because we're dividing by n plus 1, if m is minus 1, n plus 1 is 0, and dividing by 0 is not okay. So make sure the power is not minus 1. So be careful with 1 over x, basically, because that can be written as this, which is dangerous. It can be done, but just not using this method. Okay. So I've got some practice questions a bit below. We're not going to be going through now. I'm just going to show you the answer and showing how we got. So of course, the integral of x squared. We've added 1 to the power to get it to the third power, and we've divided by the new power and basically times by third. Don't forget the plus c, of course. In example 2, we've kept the constant there, 6. We've added 1 to the power and divided by the new one. We've got 6x to the 4 over 4 plus c. Here, answer in pink, it's a bit complicated. We just do each term like differentiation by itself, and the 4x squared, add 1 to the power to get 3. 4 stays there, and we divide by the 3, so we have 4 over 3. And of course we've substituted in 4 and 0. And I've done this with here, added 1 to the power, x squared. 3 over 2 still there. We divide by the 2, we have 3 over 4 x squared, and I've substituted in the 4. And yeah, basically when we add in, if we add in 0, of course, everything's going to become 0 because we'll be timesing by x, which is 0. So we don't need to take anything away, and we get left with this, and that's a definite integral there. And here we have another definite integral, 5 and 2. I've shown it here. This is square root of x to the third, which is basically a power. This is basically 3 over 2, x to the 3 over 2, which becomes x to the 5 over 2, times by 5 over 2. And yeah, we get out this horrible looking thing in true form. So that is basically integration using the power rule. So hope you understood this, understand differentiation a bit better, and look forward to the next videos where I'll be showing you more methods for integration. So thanks for watching.